Hi, welcome to Designing Google Kubernetes Clusters for Massive Scale and Performance session, where we will talk how Google and Twitter joined forces to push the limits of what GKE and Kubernetes technologies can do. And we'll also give you a set of best practices, how to think about running at large scale with good reliability and performance. I'm Maciej Różacki, and I'm a product manager at Google.
Hi, and I'm Reza Motamedi, and I'm a software engineer at Twitter.
First off, as we're going to talk about scalability, let's nail down the definition of what it actually means. If you scan the internet for explanations what scalability is, you'll find numerous definitions, but they all boil down to a characteristic or capability of a system to work with a very significant amount of resources while still being able to operate with reliability, performance, and essentially do the job that the system was meant to do. When it comes to Kubernetes, we expect that in most use cases, you will want to run on more than one cluster to minimize the risk of any potential blast radius problems with any outages. Still, being able to operate also large clusters will simplify as many parts of how you're managing your software, starting from easier ability to manage the microservices that you're running, for example, by avoiding the need for excessive sharding, to reduced operational toil on managing a fleet of clusters. There are also scenarios where simply running on a single very large cluster makes the most sense, for example, for highly parallelizable batch jobs. And last but not least, it's very useful in many cases to be able to operate in the lower bounds of what a particular technology can do, like Kubernetes, and have a buffer to the scale limits of it so that you can absorb large spikes. Like, for example, when you're running an e-commerce store, and from time to time you have very significant spikes coming from sales or events like Black Friday. When you think about companies that run at massive scale and operate huge infrastructure, Twitter is going to be one of the largest in the world. So let's listen from Reza how they are maintaining their infrastructure and how they think about its evolution in the future.
Thanks, Maciej. I'm going to briefly talk about the compute infrastructure at Twitter, where we are today and where we're going, and how Kubernetes in general and GKE specifically fits into our plans. The current main compute offering at Twitter is powered by Mesos Cluster Manager and Aurora Scheduler. Twitter embraced containers starting in 2012. We use super lightweight containers with Linux C groups. We're not using virtual machine or Docker level containers. But with C groups, we are able to co-locate most of the workloads on compute infrastructure. Currently, our compute offering is mostly on-premise, but we are extending it with computing cloud. Our customers who are Twitter engineers hire us to manage the lifecycle of their microservices that as a whole power the Twitter conversation platform. There are different categories of these microservices. First, there are stateless applications. These are mostly fault-tolerant real-time services that are very sensitive to latency. There's also a sizable amount of offline batch workload, mostly doing machine learning, which is also stateless. Second, we have services that are kind of stateful, meaning they keep some sort of state, but the state is not generally durable. These include caches and search indices and other services like that. These services are not so forgiving in the face of failure. So for them, both performance and platform reliability is important. It is also important to note that compute infrastructure was built from the ground up to be multi-tenant. So most microservices live in the same shared pool. We generally like multi-tenancy because it scales in multiple directions, from resource efficiency to operational efficiency, and also helps us with capacity management. The key win for compute team has been that all these different services use the same configuration, deployment, debugging, and management interfaces. This allows us to build tooling on top of a single platform that benefit all engineering teams at Twitter. In terms of scale, we run a smaller number of large Mesos clusters. Each compute cluster has in the order of millions of CPU cores, hundreds of thousands of containers, tens of thousands of hosts, and thousands of services are running on each cluster. Our microservices have also adapted to our large clusters, meaning that we host more than a few services that each have thousands of instances. In terms of operation, we manage and maintain all of our clusters with only 10 to 15 software and reliability engineers. With that intro, let's see where Twitter wants to go from here and how that affects our plans for the compute team. Twitter's main mission is to serve the public global conversation. For this, we need to complement our own on-premise compute infrastructure with offerings from public cloud providers. We already leverage public cloud for some workloads, for example, those that benefit from global distribution, and we expect this trend to increase over time. But as we explore using the cloud, we don't want our customers to deal with fragmented compute interfaces, both in on-premise and in the cloud. So our goal is to keep providing a unified experience to Twitter engineers. Also, as we run compute platform in more environment that offer new primitives, we see new opportunities. We can extend this standard microservice management layer that we have today across an even more diverse set of services. This means that we can onboard the remaining services onto our platform. For example, stateful services that are running on bare metal today. This will basically improve developers' experience and productivity and will eventually reduce the run the business costs for everyone at Twitter. To deal with the potential additional complexity, the compute team did a detailed evaluation and selected Kubernetes as the technology that would power the next generation Twitter compute platform, both in cloud and on-premise. This simplifies our job since compute team needs to be expert in and manage a single technology and provides a unified experience to our customers regardless of where their services are running. It also gives us the benefit and support of a vibrant open source community. But all this means that Kubernetes and GKE have to scale to Twitter needs, at least to some extent, for an acceptable migration path.
So having heard the requirements and the needs of Twitter, we set off to push the limits of what our technology can offer and meet the requirements of Twitter. Now, as we set off to document those requirements, first I'd like to explain to you the framework that we use to document the requirements and the scalability of Kubernetes in general. It's a framework that we use in this context, but we also recommend that you leverage it as you also think about your architecture, whether in the initial phases or as you're diagnosing an existing and growing system. Very frequently, when we talk about Kubernetes scale, we use the number of nodes as a proxy to describe in a simplified fashion the scale of the cluster. As your workloads grow in complexity, this becomes insufficient. You may have scenarios where you don't use too many nodes, but still hit scalability problems. For example, if you excessively use services in your cluster. So a better way to think about your clusters and workloads is through a multidimensional hypercube, where on each of the dimensions you describe the resources that your clusters and workloads need. And on all of those dimensions, there will be an envelope that wraps all of the acceptable configurations, where if you don't break those limits and don't go beyond that envelope, you will be able to say that your cluster scales so it can use the resources that you need, and it gives a healthy service to your users. The dimensions that you can see here on the screen are just examples. There's many more that you should account for. You can find them in our documentation and various materials on the topic. Here we want to essentially explain the concept, how to think about this. Also, there might be dimensions that will be very unique and specific to your particular workload with the abstraction layers and extensions that you will add to your cluster. I would like to draw your attention to a couple of characteristics of the scalability envelope for Kubernetes that are very important when you think about scaling your workloads. First of all, the dimensions of that cube depend on one another. So, and moreover, the functions that describe those dependencies are not linear and frequently also not convex. For example, you can theoretically run 110 pods on every node, but if you grow your cluster too much, then with additional nodes, the acceptable pod density will be very quickly going down, and with large clusters, you will not be able to go above 30 pods by node. The envelope tapers along each axis, which means that if you excessively use a particular resource on your cluster, then you will get much less freedom on all of the other dimensions with your workloads. The whole envelope is bounded primarily by the limits of how much data you can store on etcd. So there are points that you cannot just break with by stretching the envelope or just on one dimension. But what's pretty positive about the behavior of this envelope is that it's decomposable into smaller ones. So there are subsets of dimensions with which you can play independently from other subsets, and this way take a simplified approach to analyzing your architecture. So being equipped with this framework of describing requirements, we documented the needs of Twitter. We also engaged a few other design partners, and we worked with a broader group of customers and users who we know could benefit from operating at larger scale than currently supported on Kubernetes. And based on that analysis, we came up with a set of generic solutions, a portfolio of use cases in which we believe users really need very large scale, and we have an understanding of how the various dependencies between dimensions need to be pushed so that we offer a very good end-to-end experience for all of the workloads that users will be running on those clusters. That equipped us to set a set of targets where we want to push the existing limits of the technology forward to meet the needs of more and more demanding users. The primary dimension that we decided to improve and move is the number of nodes up to 15,000, so 3 times bigger than the currently supported limit. In terms of the number of pods, it's 500,000 by cluster. We also invested heavily into improving the various characteristics of networking components in Kubernetes, like using very large services, and many other aspects of how you run on clusters. You can look for details in our documentation, where we publish more specific information about each dimension. To effectively work on pushing the limits of the technology, we augmented and extended our testing framework through additional SLIs and SLOs, extending the test suite with additional benchmark workloads, both synthetic and emulating real customer scenarios, so that along the way, as we're progressing towards pushing the limits of the technology, we are able to effectively diagnose where we are on that journey, and are we already able to offer highly reliable and scalable service to our customers. The improvements that we implemented on that journey come in a few areas. The main one, which is probably also the most obvious, is the fact that the Kubernetes open source software required a lot of tuning and improvements that we implemented and added to the open source based stack. There was a lot of performance optimizations in various components all over the code base, Plus, we added new APIs which were designed from ground up to support large-scale and big clusters. We collaborated very deeply with communities that manage products on which Kubernetes depends on, primarily here etcd and Golang, to improve the performance that they offer to Kubernetes. And we made huge investments into the integration layers between Kubernetes clusters and GCP's infrastructure. So a lot of work went into improved logging and monitoring pipelines, auto-scaling capabilities, networking components, our control plane, its ability to configure and create clusters and manage their configuration as they grow in scale. With all of these improvements implemented and our tests to diagnose how it goes, as we realized that we built a product that we believe meets already the needs of our customers, we went back to Twitter to get their feedback whether indeed the high-performance build of GKE that we created meets their needs and will be usable for them.
So as we heard, Google has invested in rigorous scale testing of Kubernetes in general and specifically GKE, but Twitter was very much interested in running its own scale test, mainly for a couple of reasons. First, as Maciek previously mentioned, each workload profile is unique. Specifically for Twitter workloads, we were interested in scaling nodes and pods and namespaces and number of secret dimensions, but we were not interested in using some other resources like services and config maps, at least for now. This might have not been a scenario that Google had scale tested for. Second, we wanted the services running on GKE to work seamlessly with services running on our current compute setup on premise. So we decided to use pluggability and extensibility features in Kubernetes and somewhat heavily customize the control plane. We wanted to run our own scale test to make sure that our customization will also stay stable at scale. To come up with a test plan, we followed our migration strategy. We decided to create workload that would closely resemble what Twitter will eventually run in Kubernetes on-prem and also in GKE. We started with what we are currently running on Aurora Mesos clusters, but these clusters are at least 3 times larger than the theoretical maximum Kubernetes cluster sizes. So we split the services and batch jobs running on a Mesos cluster across 3 GKE clusters. As we mentioned before, adopting Kubernetes gave us an opportunity to run other type of application on compute as well. For instance, stateful applications that are currently running as bare metal services can onboard Kubernetes as stateful sets, and host level services used for host level upgrades, content distribution, and auditing can be deployed as daemon sets. In short, we profiled what's running on our current large data centers and we spread them across smaller Kubernetes clusters. We wanted to make the migration to Kubernetes and cloud seamless to our engineers. So we had to customize Kubernetes control plane to make GKE integrate with our on-premise infrastructure. We created a set of custom controllers and admission webhooks for this, and I'm going to go over a subset of the customization that we did here. We created a Twitter set controller. A Twitter set is a hybrid between stateful set and a deployment in Kubernetes terminology. And we expect all Twitter microservices to run as a Twitter set. It provides a stable numerical instance identifier similar to stateful set, but it allows us to do batch updates, similar to how deployments work. Each Twitter set can have multiple configuration per workload, which is mostly used at Twitter for canarying changes. And it also provides us with rollback on update failure, which is similar to how Aurora Scheduler performs its updates today. We also have a few mutating and validating webhooks, mostly to enforce consistent naming and labeling standards, and also to enforce security policies. For instance, we don't want to allow foreign Docker images in our clusters. We also have a node-ready controller whose job is basically to taint nodes that do not run all the expected daemons on them. After an analysis on the current on-premise workload, we arrived at the following test targets. We targeted 15,000 nodes, 600 namespaces. We added 60,000 secrets that are not evenly distributed among all the namespaces. We estimated that we are going to run 3 daemon sets and 10 stateful sets with a total of 8,000 pods. We added around 400 cron jobs, and this added another 4,000 pods. We finally added 4,000 Twitter set, which added another 80,000 pods to the entire workload. So what does a scale test look like? To minimize the inner test interference, each test run starts from a blank slate and goes through the following step. We create a new cluster, we apply Twitter customizations, we set up some monitoring, we apply the workload, and finally we collect the results. We measured these results in terms of service level objectives, or some SLOs. We carried some of these SLOs from our current compute setup since our customers are pretty much used to them. Although in practice, these SLOs highly depend on workload configuration, they give us a good baseline for comparison. I focused here on 2 SLOs here that are demonstrated in this diagram. Time to update for a Twitter set, in short, we call it TTU, and time to running for a pod, that is called TTR in short. As the name suggests, TTU is the time it takes for a Twitter set to be fully rolled out. This obviously depends on the batch size and the rolling update strategy for the Twitter set. In our test, we set that to be 20% of the size of the workload, which is a common practice among our engineers. We targeted median TTU to be below 10 minutes for a Twitter set of a size of 5,000 replicas. Time to running for a pod is a time between a pod update is requested until it is considered running after its update is finished. As the diagram shows, this also includes some overhead for deleting the old pod, in addition to a minimum ready seconds, which is a setting that you can set in your pod spec. And we set that to be 10 seconds. And we targeted this SLO to have a median of below 40 seconds. So with that, let's look at some results. We have the time to running for pod shown as a histogram on the left, and time to update for different sizes of Twitter sets across different measurements as a scatter plot on the right. We see that 95% of the pods are transitioning to running in less than 2 minutes. Note that this actually includes that 40-second baseline overhead, 30 seconds for pod delete grace period, and 10 seconds for minimum ready seconds in our test setup. Given the baseline, we see that mean time to running is 29 seconds, which is within bound. We also see that the largest Twitter set with 5,000 replicas takes on average 7 minutes to update, which is again within our 10 minutes SLO bound. So what did we learn from all of these tests? In many cases, we benefited from sharing our requirements early on with Google. This also helped Google with prioritizing future work. Another point we learned was that CRDs are stored as JSON and not protobuf structs. This is not very efficient when you're storing large objects, but there are a few tricks that you can use here. You can break up a large CRD if it contains a large array into slices. This is similar to how endpoint slices work in release version 117. We also identified some optimization points by just tuning some configuration and no code changes. For instance, we optimized the client Go that we use inside our Twitter set controller by setting the QPS and burst to improve its performance. We also reduced the load on the webhook server that we have by scoping the webhook configuration to only look at namespace resources, and this was done to avoid the flood of node level events. So as we wrap up, I'm going to give it back to Maciek to talk about some key recommendations for you if you are preparing to run large scale clusters.
Thanks, Reza. So let's take a look at a couple of recommended practices when you think about planning and running your own systems at a very large scale. As you could hear, it's important that that you test and stretch both in the planning phase and also in later execution when you're testing and building your systems. You see how you, in particular, will stretch the envelope. You need to see how your unique workload stretches Kubernetes scalability envelope, and also see whether you're not adding any additional abstraction layers or specific flavors to the workload that would apply only to you, and so it requires additional level of validation whether it will operate at large scale. You can definitely rely on us to test a set of to validate all of the native components and test a set of representative workloads, so that we really verify that the infrastructure layer that you're going to use is going to offer high scalability. When you think about which aspects of your clusters and workloads you should look into, definitely validate how are you going to use all of the native Kubernetes resources, whether you're not going to hit any limits that we documented and published. See how all of the customizations perform that you install, especially monitor what's the load and impact that they exert on the API server, and make sure they operate effectively at large scale. See also how your application itself performs at large scale, whether your pods and deployments are truly horizontally scalable, or there aren't any bottlenecks that surface when you run at large scale. You should also remember that your clusters will, in most cases, will not exist in void. They will interact with other products in your IT infrastructure, and they will exert significant load on some of them. So proper configuration, for example, of databases that your stateless microservices might be interacting with is very important to think about both in planning and later in execution as your systems grow. To effectively monitor the health of your systems, you need to define a set of SLOs that build upon the standard ones that we measure and are closer to what your end users need and how they perceive a reliability of your system. And that will give you a proper framework to monitor infrastructure that you're operating and test and iterate if you need to make any improvements into it. There is one area of your systems architecture that I would like to give you a closer look on that we did not cover before, which is networking. It's very important that you look at how your whole network layers design looks like, and monitor also how it evolves over time as your systems grow and change. Particularly all of the load balancing concepts, irrespective whether you're using Kubernetes native, you're using the ones that are provided by Google Cloud, or you bring your own load balancers. They will have a certain scalability and performance characteristics that you need to take a look at, like total number of endpoints, churn that they support, or other. You also need to account for the efficiency and performance of your DNS. If you operate and use DNS at large scale, definitely use node local caching. IP management is very important to get right, both on small and large clusters, but on large clusters that's even more impactful, as wrong IP spaces configuration can either lead to your clusters not being able to grow beyond certain limits, or on the other hand, possibly using excessive amount of IPs without the necessity for that. As last recommendation here in this context, we always recommend that you use regional clusters for production, and for large-scale private ones that offers the best reliability, availability, and best network throughput between the master nodes and the rest of the cluster. Whenever you hit any problems or you have any doubts, please reach out to us. Your account team or our support teams are the first line of communication that you can engage with, and they will involve broader groups at Google that will be very happy to step in and help you at any stage at which you might be with your work at running at large scale. To wrap up, I wanted to make a couple of final remarks. As you could hear, 15,000 nodes are coming to GKE. We will be rolling them out on top of release 1.18. We'd be very happy if you decide to use them, and we're very eager to hear any feedback you might have about them. If you have any questions, feel free to use the Dory, and also here on the slide you can see our Twitter to also send us a direct message. With that, we wanted to thank you and wish you good luck at running at large scale.
And I also wanted to thank you for tuning to our video session.